time too. This is probably because the temperature goes up in the actual XRT measurement, while the temperature is kept almost constant at 10 degrees C in the loading ratio measurement. So probably the chemical absorption of tellurium is strongly influenced by the electrolyte temperature, and then we could go into the region or somewhere like 4.94 or 4.95, which we attained in the loading ratio measurement. So after this, we decided to go new materials, which is palladium rhodium. And I'm showing you by this figure that it is known by the work by Baranowski, I can't read this, and also by Flanagan and first in Journal of Physical Chemistry in 1973, that when we increase the content of rhodium in the palladium rhodium alloys, we decrease the lattice parameter of the alloy from 3.884 to something like 3.816 at 80% rhodium palladium alloys. And then they reported that the hydrogen rhodium ratio expressed by H/M is almost 1 at the content of 20% or 30% of rhodium palladium alloys. So we ordered these palladium rhodium alloys to Johnson Matthey. And I'm showing you here some X-ray diffraction data to show the change of lattice parameters of our alloys, which was only 5 and 10%. We are going to have 20 and 30% rhodium palladium alloys shortly, but if we plot the lattice parameter as a function of atomic percent of rhodium, we can see very coincidence between what is called Vega's rule to show the linear relationship between the lattice constant of alloy and each respective palladium and also rhodium lattice constants. So the loading of palladium rhodium alloys for 5% rhodium palladium alloys in 1 molar DIO. I'm showing here the change of d over m as a function of time, when we change the current density in stepwise manner, shown in this way. So the experiments lasted for nearly 120 days, which is still continuing actually. But what I would like to point out is the d over m is very close to 1 in this range. After some current density, d over m comes down. If we show the similar data, the same data, with the data for hydrogen ore voltage, we have this. But although we have not excluded the ohmic ore voltage due to solution resistance, so this is the total hydrogen ore voltage, including ohmic ore voltage. The reason why we cannot eliminate is we are still continuing this experiment. The temperature during this period, which increases in a stepwise manner. So the reason for the deloading slightly after loading ratio 1.0 is probably because of the higher temperature in the electrolyte. So if I summarize this loading data, as a function of current density, we have loading ratio nearly 1, nearly 0.1 amperes per square centimeter. Then it goes down to something like 0.94. The excess heat for this high loading ratio regime, we have this one, the change of excess heat as a function of time. So up to the loading ratio of 1, we see no excess heat, but very embarrassingly, we are starting to see excess heat when the alloy is actually deloading slightly. This is more clear to show the actual dependence of excess heat as a function of D over M. So it decreases sharply in this region. Probably, I should say, this is a very embarrassing data to show the decrease of excess heat at the region where it is not supposed to behave like this. But if we plot the same data as a function of current density, we have no problem to show the general increase of excess heat as a function of current density. So we thought maybe we should try 10% loading paradigm alloys. With 10% loading paradigm alloys, we have this. I'm not showing the actual data to show the time dependence, but I'm showing d over m as a function of current density. So you can see clearly that d over m on this 10% loading paradigm alloy shows loading ratio higher than 1.0 nearly all the time. But we have this at the moment. I'm showing the calibration curve obtained by nickel electrode and red points observed by using palladium cathode. So the palladium are very happy to sit on the calibration curve. So if we plot the excess heat as a function of current density, we have this, no excess heat, and also if we plot as a function of d over m, again, naturally we have no excess heat in this very high loading ratio regime. So, to summarize all the data, including the data by using 5% loading palladium alloys, we have this excess heat as a function of deuterium loading ratio. So, if we look at this data, we are not sure if deuterium loading ratio is a very important factor after some certain value, because partly because the accuracy of our measurement, the data points are very scattered, and we still do not understand why this palladium only gave much higher excess heat compared to other palladium materials. And the same data as a function of current density, which is much more systematic. And we haven't tried to plot all the data as a function of cathode ore voltage, because the data for the cathode ore voltage are not still available for this 5% loading palladium alloy electrode. So these are all what we have got up to this point. So as far as the reproduction is concerned, we will say that we could not reproduce all data in a quantitative way, but we could say that we can reproduce all the data in a qualitative way, scattering between 5% to probably 35% in terms of excess heat with respect to the input power. So, as I promised, I should say something about conclusive so factors controlling loading ratio. I must actually leave this point to Ms. Akiko Kubota, who will talk about the summary of all activities in the loading experiment. But what I would like to show what she is not talking, she's not going to talk about, which is this one. Recently, we have observed a very strange behavior of the palladium from mineral materials to show the very strange change of loading ratio. Then, as a function of current density, loading ratio is somewhere 4.86. Then, close to 1 ampere per square centimeter, it went up. Then, when we go back to lower current density, even it went up again. And we did not understand this. This is very clearly seen on this raw data to show all the data during the electricity period, which is nearly 4 months. So up to here, we have a very steady increase of loading ratio as a function of current density. But when we decreased the current density at this point, the loading ratio went up without taking much care of the decreasing current density. And we have similar tendency actually by the Johnson-Massey palladium electrode, which is shown here. So the loading ratio, current density, then it goes to something like a small minimum, and then went up again to the value higher than 4.9. In this case, we are seeing the loading ratio of 4.94 at nearly 700 milliamperes per square centimeter. So, lastly, I'd like to comment on what we feel about factors controlling excess heat. First of all, last year we thought that DOPD was the most important parameter to control excess heat. Then we realized that the current density is also important. And then this year we are seeing that the cathode overvoltage may be some other factor controlling excess heat. And also, what we do not know is the effective temperature. Although the effective temperature may be very significant, according to the very surprising data by Professor Fleischmann and Tones showing the very high excess heat generation at the condition of the electrolyte boiling. And we do not know anything about the effect of impurities. But as far as the loading is concerned, lithium is not good, which will be shown by Ms. Akiko Kubota on the Thursday morning. And then the people at SRI are talking about time, which means we should be patient. But we see sometimes the effect of time, but we do not see in many cases, or maybe we might have just passed this time period without noticing the effect of time. So we would like to investigate the effect of these parameters systematically, but unfortunate condition is the number 1, 2, 3, 4 are not totally independent in our experiment. When we apply current, it determines deuterium loading ratio, and it determines cathode voltage, and it even determines, in many cases, the temperature in the electrolyte. So we are thinking that it will be better if we can conduct or analyze our data at constant deuterium loading ratio, or constant current, or constant cathode voltage, or constant temperature. So we have 4 variables. So maybe the analysis could be very difficult, but if one of these parameters are really important, there is no reason why we shouldn't do this sort of systematic investigations. And also, we do not know anything about utility and time and so on. And probably for 7, we should say something about the effect of non-steady state in the palladium cathode, which we do not know at all at the moment. But looking at this data, I would say we now know much better than last year. I mean, last year at the NAMA conference. And I hope you can understand what I'm saying. We know much better than last year through all our data which I presented this morning. Thank you very much.
I think this is a very, very provocative paper, and there were a couple of things that struck me. A curious thing about your loading ratio is that as you varied the different samples, some of them seemed to go up linearly, and some of them didn't. There was one in particular, I think the TNK, that almost hit about 0.86, almost straight up. A thing that has been interesting to me in particular, from the very beginning of this, has been the role of crystalline order and the dimensional implications. It suggested that as you go from one sample to another, especially given the way that you measure things based upon pressure, the degree of crystalline order might be changing. Now there's the alternative method of measuring loading, which involves the resistive measurement, which does sample crystalline order in a different way. I was wondering if you wish to comment on that, if you looked at some of these other ways of measuring the load.
Yes. Actually, we compared our loading data by conducting the resistance measurements in the same cell, by combining the resistance measurement and pressure measurement.
I see.
Actually, I shouldn't talk much about it because this actophoto will be talking about on other mode, but I should say just simply they coincide. The loading data from pressure.
They coincide. Yes. Okay. Well, the other question that comes along here is with regard to the degree of crystalline order and the importance of crystalline order. I would suggest that that may be an additional item that you might include on the list, and that it would be very interesting to see what these things look like afterwards. I don't know if have you done any sort of post-analysis of how these electrodes have evolved?
First of all, we were very interested in seeing many cracks.
Exactly.
In the very early stage, we see many cracks. But currently, we haven't seen any visible cracks. So,
I'd be particularly interested in the cases of thyroid versus
But that is what people are saying. But we haven't tried anything at all to add any impurities on parts yet. Although we do know the actual impurity concentrations on each palladium electrode. But we do not know actually what if any of these impurities in the cathode are playing any particularly interesting or important role.
I'd like to suggest that an interpretation of your dependence on DPD can be given something like this. As you go up past round about 0.65 and appropriately 0.83 or 0.85, you begin to get a certain amount of internal damage. And I'll show in my paper this is so. A certain amount of internal damage gives you increasing numbers of dislocations, of which the absorption of hydrogen deuterium is particularly strong, giving you deuterium to combine with, which doesn't have a Coulomb barrier, just isn't charged. But of course, if you go past that, cracks develop which reach the surface. Directly they reach the surface and all's finished. The deuterium begins to escape, and down goes the DPD.
It's a very interesting paper, which I enjoy very much. Two comments to make. One with respect to thiourea. We found, as have many others, that indeed the same result occurs that with thiourea you can achieve a very high deuterium to palladium ratio. But we found that after a number of days, say 10, 12 days or so, the effect was lost. And in our experiments, and of course we had a high cell voltage in U because we were always electrolyzing water. But in our experiments, the effect was lost, and often the loading ratio went down less than you would get without that. And we think the thiourea was oxidized and destroyed on our anode. Another point was that there were the effect of overvoltage versus loading. We always felt that probably the real important factor is obviously the chemical potential of palladium deuterium in the lattice, which is reflected by the overvoltage. And if we could measure that accurately, we might have a good criterion. The issue, of course, is that there are always surface films that build up after some time, and that these add to the overvoltage. And these surface films can be quite significant. And we've observed at times when events have occurred that these surface films have been flushed off from the overvoltage, or at least the cell voltage changes significantly. So what we need is a way, obviously, to measure the true overvoltage of the electrode, a way to distinguish between the solution resistance and then the surface film resistance.
Well, about the thiourea, I agree with your comments. We may lose the effect of thiourea if we have thiourea in the systems which actually oxidizes the walls oxygen atoms, which is a very destructive condition for thiourea. But for fuel cell systems, it does not happen. The potential of the fuel cell anode remains low enough not to oxidize thiourea. And I forgot your second point. Overvoltage. Yes, overvoltage is a sum of the actual interfacial overvoltage and solution overvoltage. And solution overvoltage can be measured separately by the current interaction method well known to electrochemists. So it is not difficult to separate the two actual overvoltage from total overvoltage measured.
We're going to take one more question, and then with KG's indulgence, I'll make him stay here and answer more, but we will have a break, and I want people promptly back here 10 minutes after the schedule has asked at 10:50. But
see lack of heating. And also, if you have surface crater, to see if that correlates with your excess heat. And finally, using the scanning electron microscope, often these surfaces have either whiskers or dendrites or pyramids built up, many of which have a sulfide layer. Particularly if you have some iron impurity, there's a tendency to get iron whiskers covered by sulfide. And if you handle the specimens carefully, there might be a lot of information from scanning electron microscopy observation of the surface with respect to those of overvoltage.
Yes, I agree. We do very good teacher.
Give people an opportunity to go up to the refreshments outside, but we'll carry on with the questions for those who wish to stand listening.
I'm working with a group of professors currently at the ISCCF-4 laboratory in Rome, and I will report our activity, more exactly our results of research on the behavior of a PD membrane during the deuterium and electrochemical loading and the excess heat production. Well, I will make a little bit of history. Well, there has been a development of the NEA-92 research activity after the Nagoya conference. After the good results came last year, we started a correlator research with two other institutes, more exactly the Institute of Solid State Physics of the National Council for Research, in order to perform X-ray scattering and so to determine the loading ratio of our cathode. This work will be reported by Dr. Felici on Wednesday afternoons in the panel session on special topics. At the same time, we are starting right now, during these days, another collaboration, or better say, correlator research with the National Institute of Nuclear Physics with Professor Moroni in Bologna, aiming to make neutron measurements at the Gran Sasso laboratory. The Gran Sasso laboratory is a particular high-energy laboratory under a mountain, the Gran Sasso. It means about 2,000 meters of shielding. And Professor Moroni and his group will try to perform these neutron measurements also with energy resolution. Both these two research are using the same cell setup that we used and presented last year in Nagoya, and it's always the same cell setup that we used for this year. Then we are in contact with the group of Professor Megoli, always of the National Council for Research. This group is quite involved in studying and transporting the fusion of deuterium and PD lattice. And I remind you that this group recently published the diffusion coefficient of the deuterium and hydrogen and vanadium lattice. This is a good contact, and we are discussing on the year 2 and trying to get a better understanding of the transport of the deuterium. So, the outline of my talk will be the state of art of the ISCCF-4 laboratory, our improved matrix system. I will speak about the results obtained this year on heat excess and on the dynamic of the deuterium and the PD lattice. Some notes on the materials since 1991, our group decided as main goals were and are to investigate the transport of deuterium in PD lamps and the achievement of high loading ratio and possibly its correlation with its production. Since 91, we tried we performed a fifth generation calorimetry experiments reported in Nagoya with a particular cell setup. This year, in this conference, I will report on the second generation experiments, and shortly at the end, I will speak on the third generation experiments, which we will try to perform in 94, including the helium-4 detection, aiming to obtain as more as possible clean experiments. Well, just a few words, a few minutes on our approach. Well, as I told you before, we are quite interested in the electrolytical loading. For this reason, we make electrolysis with palladium electrodes in a solution of LiOD 0.1 M. We use palladium electrodes in order to regenerate on the surface of the cathode a new sheet of palladium. In such a way, we can avoid contamination, pollution, and so we have always a new surface. The PD cathode is a particular cathode. It acts as a membrane between a gas and LiOD system. As you can see here, the cathode, this one, is supported by a glass pipe which goes inside the cell. So inside the glass pipe, we make vacuum, it's always evacuated, and so we can measure the flux coming out from the backside of the cathode. Well, with the flux measurements, that's the pressure measurement, we can have an idea of the loading ratio at the gas surface cathode. Well, in front of the cathode, we have the anode, which is naturally in the electrolyte, and so we make electrolysis. This is our setup, the cell setup. We make also a flow calorimetry, and we, in principle, just a few words on the cell setup here. We have a glass coil going inside the cell, surrounding our electrodes, and we measure the difference in temperature between the inlet temperature and the outlet temperature. Our maximum error in doing this calorimetry is around plus minus 50 milliwatts. I will talk more about this later on. So, here are some preliminary results on the loading ratio evaluation. As I told before, this particular geometry allows to follow the cathode charging. So the equilibrium pressure behind the cathode gas surface states the dPd ratio. We can measure the atomic flux, and so we can find a relation with the phases of the charging. And then we have seen last year an anomaly in the pressure behavior. Would you like to show you this plot? I hope. Yes. So, on your left, you have the pressure, which is this dotted line, with this solid line going up. Here we have the beginning of the experiment time, and then on the right, you have this is correlated, we believe, is to the alpha-beta phase. The flux here, the flux rate is smaller and lower than in the alpha phase. And then after 36 hours, in this case, yes, 36 hours, the flux back is growing more and more, and is correlated to the beta phase. Well, this was an experiment for gamma for X-rays measurement, and here we reported 3 experiments, all with this technique. During the alpha phase, we see quite high flux, and during the alpha beta, 0.8, a decrease. Then we see a very high flux level. We have seen the same thing for another experiment which we performed in October this year. Last year, the 92 experiment 3, we have seen a flux behind the cathode and the gas surface related to the beta. And then during the heat excess, we have seen an absorption. From the gas side, some deuterium went inside the cathode. The 93 2 experiment is the only experiment with heat excess production, and we have seen a beta phase clearly, and then before heat excess appeared, we poisoned the gas side surface with the CO because we were interested to see the behavior. Well, from this analysis, we believe that the flux variation is surely correlated with the phase change in the cathode. And this will be also, we are trying to do at the same time X-ray measurements, and on the electrolysis side. Why? For this reason, because if we measure the flux and we know the diffusion, the coefficient of the diffusion, we can approximately evaluate how much is the concentration on the electrolysis side. In our experiments, on the gas side, we have measured always the concentration of the DPD ratio between 0.65 and 0.68. By taking into account this expression, we evaluate on the electrolysis side concentration ratio quite high, between 0.75 and 0.8. On the first experiment with X-ray scattering, we really measured on the electrolysis side, Dr. Felice reported that DPD ratio of 0.8. So it's quite interesting for us to go further with this kind of research. We think that with this membrane technique, we can follow the charging at least up to 0.75, 0.8. Well, a few words on our improved calorimetric system. It's based on flow calorimetry. We make a differential measurement of the delta T, the inlet temperature, and the outlet temperature. We make a calibration in situ, means that we have a heater inside the cell, and we make our calibration, taking also into account the boiling fat and the cooling water flux. Our cell is inserted in a Q-wire, and this system is once again located inside a very big box. So we are free from room temperature variation. It took a lot of time to improve the system, but we achieved a very good, we think, sensitivity. 3 watt to 400 degrees corresponds to increase to 1 degree Celsius. And we have a maximum error of plus minus 50 our system can work at 30 degrees or 50 degrees Celsius. We can set up our box temperature at these two temperatures. We are quite interested in doing measurement of the loading ratio and heat production at high temperature without going up very, very high current. So with this system we can measure, we can see the dependence on the temperature. Well, just wanted to show you, this is on the left, the difference between the output power and the input power, the delta, so-called delta power, for at 5 watt input power. This is the last, the number 4 experiment. And as you can see, we have a new value of 9 milliwatts. It's corresponds to 0.5%, and we are very happy with this system. Well, here are the results on the heat effects. This is so-called experiments of the second generation. We had 4 runs. The 4th one is running now, and I don't know if it's still going on or if it produces heat effects. But up to now, only one produced heat excess. This heat production is surely correlated to the high EPD ratio because we measure it. It's about 0.75, 0.8. And we have seen maximum value between 4 and 4.5 watts. The experiment lasted a long time, almost 1 month, and I'll show you the latest hours. Here on the right, on the left, we have the delta power, and on the left, we have on the right, we have the cell voltage. Well, during the first 10 hours, we had a constant current, about 50 milliamps, and we saw just a little amount of heat production. We already saw heat production the days before. The heat production was around 10 days. Then we increased the current in order to follow a relationship with the current, the heat production current, and we just rise up the current, and also the heat rise up. The heat is the solid line, as you can see, and it was about 8 hours. And then we rise once again the current up to maximum 1 ampere per centimeter. Well, we had heat excess power of 4.5. At the same time, here you can see the cell voltage or input power is going down. And okay, it goes down because concentration will become higher. But this is a clear evidence of heat production. Well, this heat production corresponds around 8% of input. But as I told you before, we already have seen heat production 10 days before. And then we have we have observed relationship between the current density and the heat production. I think this relationship is also been observed from Dr. Lucy before, and also I think the next day we will discuss about that. Well, we have compared this experiment with the experiment last year, so-called 92 experiment 3, where we the X here plotted, and the black points are this here with continuous current. As you can see, there is a relationship. We observe a relationship with the current, and it turns out to fit very well also with the data from Professor Watson. We don't understand very well why here a very low current density. There is a big difference. It could be related on material problems because this patch, the 92 palladium, is an old patch, and the 93 palladium platinum is a new one. So it could be correlated with this different patch, or maybe it could be the hydrocurrent technique. But we think that after a certain current density, after 200, 300 milliamps per square centimeter, the bulk is working very well. We achieved also around 100 watt cc. And that's it. Well, some notes on the materials. I just mentioned before that we had heat excess, difference in heat excess, because of different material patches. And we have something now during these days, running experiments, and in order to understand the difference and the influence of pre-treatment, cleaning, environment of the annealing, patches and impurities, and to study their influence with the thermodynamic entropy. We have preliminary results there. We have seen with X-rays that the material patches are different, but we need more time to go further with this research. We want to make a database and to understand better the transport. Well, just showing you only what I mean with database. We have 7 experiments, and we want to see the influence on the annealing, the environment, the annealing in argon atmosphere or in vacuum, the different batches, the Johnson matrix, the Tanaka, the old batches that's here, and then the maximum pressure achieved with this membrane technique. And there are other parameters, and it's before we can understand, we need more data on this. Well, only a few words on what we call modeling, actually theory. We are trying to make a thermodynamical approach to the problem of deuterium diffusion and PD lattice. For this reason, we are working together with Professor Henry and also the other people. Our aim is to make a preliminary calculation on the diffusion coefficient versus the concentration. Well, this means that we are trying to understand better what role plays the chemical potential and other related parameters like enthalpy and entropy parameters that this morning Dr. Fleischmann talked about it also. We are just starting now, and I think that the next year we can have first results on that. Well, few words on our conclusion and future plan. Just I will remind you that that we work always with this approach, membrane approach. And I think we think that this approach is a good one because we had good results, and we wish to go further, achieving a higher physics power. For this reason, it is necessary to do our experimental change also the temperature. And this third generation experiments should include the in-field measurement detection. And we are aiming to try to do it as small as possible to make a clean experiment. Professor Cossetti is going to show that it's not so easy. Also, Dr. Meyer showed that in the past it is not so easy, but we have confidence to try this experiment. The last point is the material science, so-called materials. We are thinking that this database on particular feature of the materials is important. And this takes a long time and is a strong collaboration also with the German Semantic Society or the Janaka, with the producer. And to do this database, we are going to contact our colleague from Yakazacha, particularly able to work in the new science, technology, materials, and so we think that we can have good results. This is our activity. I wanted only to say that we are so many, just here, we are 4 people working all the time in Professor's Committee, Dr. very, very busy. So we are not able to do everything in the insurance. For example, we didn't perform because it takes quite our man and time. But we hope that with the collaboration with Dr. Felici and Professor Roni, we can obtain good results. Thank you very much.
This is a question. Normally, when beta crystals start to form in the alpha on the surface, the hydrogen or the deuterium pressure should be absolutely constant until you have an all beta surface. The fact that you have this period where it's not constant, it's lower slope, but it's still not flat, means that either you're creating a lot of strain, allowing more hydrogen to go in, or possibly you're cracking deep into the alpha, create a new surface down deuterium. In either case, it would seem like this would be an interesting thing to look at as far as the excess heat. Is it a function of how flat that alpha plus beta pressure is?
Well, the flux coming out from the alpha beta phase has a very low rate. You have to think that there is also a leakage of the system. For this reason, it seems that it's decreased during time. But I agree with you that this crack inside the catheters are extremely interesting. And indeed, we have seen that this element has worked. We really saw that there is a big difference between electric working very good charge, just 0.75, and other electric didn't charge, they didn't work. But we are asking now to our colleagues in Yakazacha to make these studies of metallurgy, and we are not able to do that.
Are you going to do some testing on beta phase alloys, silver alloy?
charging. I think that our first preliminary answer to this problem is the Japanese measurement of this one. And also, Professor Mabel is working with palladium volume, and this is an open question. And maybe we will see the next year what if we work. For the next year, we are aiming to make also this scheme for children. Actually, it takes a long time.
I have measured the membrane technique with electrochemical on both sides. Now, admittedly, this is going to be iron, but there's a message in it. We were able to measure the dislocation content with positive quantum annihilation. So we detected on both sides of the specimen. They were very well in specimens. We could detect the arrival of hydrogen on the backside, so we could measure the time. Okay? Now, we found out the polishing of the surface had a tremendous effect on the rate of diffusion of the hydrogen through the specimen. The 20, we can measure the dislocation content in the outer 30 microns of the specimen. And that was typically produced from a highly annealed specimen by mechanical polishing with diamond. Only 95 microns or half micron. The diffusion coefficient, when we did this, okay, decreased by 1 order of magnitude. Okay? And as we chemically remove this dislocation content off the surface, we got the diffusion to be established to be identical with that in gas phase. Without that, there's a tremendous spread due to dislocation and the polishing techniques. I don't know if this exactly relates to your particular question. There's a message for all of the people here that they have not been paying attention to what mechanical damage does. Mechanical polishing, even under the best of circumstances, does to the diffusion coefficient.
Well,
It's well known that Deuterium is trapped in the dislocations in play.
well, I agree completely with you. I didn't want to speak about our results. We have seen clearly that if we activate our surface, our cathode with the temperature, we just anneal the cathode up to 970 degrees. There is a big difference on the deuterium transport. And we are thinking that also this location play a very important role, and we have to go further. We change the dislocation, and so we have to go to very high temperature, at least 0.75 of the melting temperature of the palladium. We don't know exactly. I am not a specialist on this field, but my belief think also looking at the dislocation is very important. But I think the meteorologist can tell us more on this problem, and to make a really good database takes many experience.
Please show the the motivation for between the current density and the excess heat. Okay, no problem. You said maybe that even the very low current density, you find some excess heat.
Yes?
Yes.
Last year we find
Yeah.
excess heat.
Maybe according to your current measurements preciseness. But I want to know excess heat in your discussion?
I really don't understand what you mean. Model of the heat.
Usually we have a very appreciable, evident threshold to get excess heat as a function of current density. But you show in the very low region, current density, also you can find some excess heat.
Well, if I will understand, I will have to finish just the answer. Last year we have seen excess heat at a very low current density. We don't know whether the thickness.
Well, may I just make a point here, because it's still the same point. The results you presented last year were done with a particular protocol, namely a high current followed by low current. Those results may be an expression of extension of what we call heat after death. You simply have to drive your system to generate heat, you're on a continue your measurement cycle, and you're getting heat at a lower current density. And in fact, you find that if you have this program to decrease the current density, you can maintain excess heat production at a much higher level than you would if you simply use that low current density continuously. This is a reflection of the effect of the protocol of the experiment and the excess heat generation.
That's right. I didn't explain it very well.
Thank you very much. Thank you. I am present an overview of the work that our laboratory is doing presently and in the recent past to investigate calorimetric effects, loading effects, and potentially nuclear effects in the deuterium-containing system. The list of people who are currently working in the SRI lab are presented here, and I owe a tremendous debt to each and every one of them. Having just looked at the list, I noticed that I made a grievous omission. My boss, who was in the audience, actually doesn't have his name on this list. I guess I'll pay for that. The work was supported by the Electric Power Research Institute and with Tom Hassel's active help, guidance, and support. One of my colleagues, Steve Crouch-Baker, likes to say, an experiment is done for one reason and one reason only, to test a hypothesis. It looks back and investigates the hypothesis that which we embarked upon this strange research program. That hypothesis was that there was an unexpected and unexplained source of heat buried somewhere in the deuterium-palladium system, and that this source of heat was observable under the condition of high loading. Suggests experiments both in the field of loading to understand how to put, to insert and maintain high loading levels of deuterium inside the palladium lattice, and calorimetric measurements in order to investigate this potential heat source. The results that we have obtained and have discussed previously, excess heat and excess temperatures are indeed observed in mass flow and heat flow calorimeters. That these heats, energies, and powers are not consistent with known chemistry or with any artifact that we have considered. we find that loading is indeed necessary, but it is not a sufficient condition for the observation of excess power. The current is important, or the current density, or the electrochemical potential of the deuteron in the lattice, related properties. Temperature is certainly important, and not an orthogonal variable, as Katie pointed out this morning. There seems also to be some time-dependent process, so that one must establish a loading, maintain a loading, and probably also maintain that loading at high current densities for a significant time before one expects to observe any anomalous heat source. If we say that heat is observed and that this heat is not of chemical origin, we then may propose a second hypothesis, that this heat originates from an unexpected and currently unexplained nuclear process. The experiments that we are performing now to investigate this potential nuclear source, we're really trying to observe, hopefully, a temporal and quantitative correlation between excess power production, excess heat production, and the production of some known product of a nuclear process. Unfortunately, we don't know what that product is, and we must explore a rather wide range of potential products. We're setting up and have now established a very useful gamma and X-ray spectrometer. We're presently establishing a neutron spectrometer to go after the traditional products of nuclear processes, to determine not only to what extent they are present, but to what extent they're not present, with some sort of upper bound on the production of these species. We also have in mind at least a charged particle telescope, not conveniently used in electrochemical experiments, which most of our experiments presently are. We investigate tritium as a potential product, helium as a potential product, and isotope shifts of deliberate additives to the lattice, such as lithium and boron. The lattice constituents itself, palladium, these necessarily, at least in our hands, are post-test analyses. This year has been very much a year of building for us, particularly since we are not known for our expertise in any of these areas particularly. We were trying to establish a capability. And we have built these systems but have not run them to a sufficient extent to be able to say that we have confirmed in our experiments the nuclear process. Neither, really, have we given these experiments sufficient time in order to make a proper determination. Hopefully I'll stand up for you next time to either confirm or deny this hypothesis. What we did find is that separate systems are difficult to optimize jointly. That is, if you do everything right to do good calorimetry, you can't also do everything right to search for these nuclear products. And if we take a compromise in either the calorimetry or the nuclear detection, you can then only look for one potential product at a time. Maybe we'll get smarter or with some help be able to do a better job. But we're attempting to optimize one parameter, that is, an optimized calorimeter, and bring some sort of optimized nuclear detection to it, or an optimized nuclear detection system and bring some sort of compromised calorimetry to it, to define lower bounds on potential products and to make accurate determinations of product energies using spectrometers in order to aid the theorists in their understanding. We've built a rather impressive in terms of cost and mass gamma spectrometer, and Nada Jevtic, who's operated with the guidance and help from Kevin Wolf, would not forgive me if I didn't describe what this system is. I'm not going to go down the list of its functions. If you wanted to discuss it with me afterwards, I'm happy to. Basically what we have is a 4-inch tower of lead, some 2 or 3 tons of lead in a cylindrical configuration, the pink thing on your slide, inside of which is sodium iodide Compton suppression annulus. into which, inserted from the bottom, is a germanium, liquid nitrogen-filled germanium detector, ultra-low background detector. And the red space here is the working space for a calorimeter. There is a calorimeter running inside the system presently. We have not, unfortunately, as yet, either obtained adequate loading or excess heat production in the system. We've beaten the background down to a pretty decent level, in fact. This is a slide that Nana prepared for me. It took her about a day and I have to present it. The red is the background without content suppression. The black is the background with content suppression. Basically, our background is 1 count per second in the range of 3 kV to whatever we've got it out here, probably 2 or 3 MeV. Presently developing a system which is an unashamed plagiarism of Kevin Wolf's neutron detector, NE213 system, 2 detectors operating in background foreground mode, where we'll be able to resolve the energy of neutrons. The approach is the same as for the gamma detector, basically. Do everything as well as we can for the neutron detector. Active shields, passive shields, calorimeter inside the system. In doing that, we can't run a mass flow calorimeter in a 1-ton bath, which we do when we're doing the job as well as we can. So there's some sort of compromise in calorimetry, which is inevitable in process. We look for tritium, ex situ, and all our measurements. We have our own X-Trail C50 mass spec with about 1 ppm resolution, baseline separated deuterium helium to take grab samples to look for helium production. We've also been sending samples out to the Bureau of Mines in Amarillo, Texas, who have a much better sensitivity for helium in the presence of deuterium, about 1 part per billion for helium-4, better than 30 parts per trillion for helium-3. So we take grab samples, send it out in metal flasks, and send it out for analysis. It's a quick overview of the nucleus stuff. I'm now going to talk a little bit about the second phase of our project, which is really the first phase of the project, the loading studies. We've been using, as you all know, in situ resistance ratio measurements to determine loadings. We find this to be a very satisfactory and reproducible method, easily implemented in a computerized data acquisition system to give online measurements of the loading. We have 2 different experiments. Excuse me, a farm of 10 electrochemical cells which we run in electrical series all together in order to explore variables for the loading. We also have a movable wire. As you all know, all of you have attempted to do experiments in this field. If you take 2 different sections of palladium wire cut from the same stock, put them in identical electrolytes, run them electrically in series with the same current passing through them, you will not get the same loading, you will not get the same interfacial impedance, you will not get the same overvoltage. The question is, what is the element of irreproducibility? Is it contained within the metal? What we have built is a system which allows us to interrogate successive sections of a single piece of wire with either identical or different metallurgical pretreatments in order for us to understand better this element of irreproducibility, which leads to irreproducible loading and therefore irreproducible accessing results. I want to just show briefly some results to highlight 5 points which I think are important. The differences which have already been mentioned before by the previous speaker, the difference between different batches, different lots of palladium from the same supplier, nominally identical. Anode selection, surface modifying agents, where we have used and found successfully additions of aluminium and silicon, which form aluminates and silicates in the electrolyte, and the role that this plays in Fritz Will, who is here to obtain high loadings and apparent tritium production, who will speak about that this week. I personally do not believe that this method actually permitted increased loading of deuterium or hydrogen into the lattice. I believe that the cold work done by periodically stripping the hydrogen out of the lattice and reinserting it, much to the point that John Bachers made this morning, created voids within the metal, which would allow more hydrogen to go into the metal, but not necessarily into the lattice sites. I'm able to confirm that this alternating polarity method does indeed cause increased loading of hydrogen into the lattice sites, which give rise to the resistance change that we measure as a determinant of loading. I also want to speak a little bit about annealing conditions. Just to remind you and why we care about the loading, this is an augmented slide of something that I presented before. This is the resistance ratio versus loading curve for deuterium and palladium. The resistance ratio, of course, starts at 1, is defined to start at 1 at a loading of 0. Goes through a maximum of about 2 at a loading of about 0.725. Then it comes back down the right-hand side. Several things are salient about this. One is the electrode will never spontaneously deload much beyond this maximum. As long as you continue to evolve hydrogen on the surface of palladium, it sits there bathed in a 1 atmosphere hydrogen environment, it will never spontaneously deload and go down the left-hand side of this hump. So, as a qualitative indication of loading, we can simply take the reduction of resistance as an indication of increased loading. Whether you have a qualitative or quantitative understanding of this curve is not so important. To us, an improved experiment is one in which we traverse the maximum and go down the right-hand side of this curve, and the further you go down, the better off you are. What we have discovered by retrospective analysis of all of the experiments that we performed is that if you go beyond this line, the pink one that I've drawn at a loading of 0.95, in every case where we have achieved loadings beyond that line, the cathode has been made to produce excess power, excess heat. The green line, in no case where the electrode was loaded to a maximum value significantly less than 0.9 have we observed excess power or heat. The zone of importance, unfortunately, is this region between 0.9 and 0.95. In this zone here, the cross-hatched region, some experiments do and some experiments don't. So what we really want to do, we don't care about loading. All we want to do is get our loading down to there, and then in every case we'll be successful. That's why we're interested in loading. I mentioned the moving wire apparatus. I want to show you a brief sketch of it. It's a movable wire. Basically, you start with a 1 meter spool of 1 millimeter palladium on this, go through an etching bath, it's conveyed down through a annealing furnace where we maintain a controlled environment, controlled temperature for programmed time to establish a uniform pre-annealing treatment of the surface. We can also pass gases through here in order to deposit species on the surface during or after the annealing process. In no hands, the wire carries on through a region of preconditioning, where this section of prepared wire can be preconditioned in the way that we choose, and down into the electrochemical cell. So this wire has current contacts at the top and the bottom, and 4 solenoids drive contacts in and out. So this system drives contacts in to touch the wire and then back out again. So we can measure the resistance between this plane and this plane to determine the loading of that section of wire. We do a current time sequence on this cathode and measure the loading, voltage, time history of a particular section of wire, and either repeat it with the same wire or move them in differently prepared or identically prepared dedicated section of wire into this electrochemical zone for interrogation. I'm not going to discuss the results of that today. Here's a representative loading curve from which you'll be able to understand the results that I'm going to present. As I discussed before, resistance ratio goes up through a maximum, down the right-hand side, and hopefully down the right-hand side as far as possible. For reference, if we can get down to about 1.5 on the right-hand side of the maximum, that is a resistance ratio which is associated with a loading of approximately 1.0. A very good test of the ability of a particular surface preparation to facilitate loading is the response of the resistance ratio to increasing current density. If, on applying increased current density, the resistance goes down, you can be fairly well convinced that one, the cathode is able to absorb more deuterium, and obviously that we're on the right-hand side of the maximum and not on the left-hand side. There's been some discussion. This curve obviously is life-valued. Value A and the value C is the same resistance ratio. The question is, how do you know that you're at C and not at A? Well, the increased current test is one. The other method, though, is that we frequently strip the cathode. So you'll make the cathode anodic, go up through the maximum, down the other side, and then make it cathodic again. You'll traverse the maximum and go back to the right-hand side. So you'll see this sort of double value function is a very good indication that you're on the right-hand side of the maximum. The degree of loading cell is one that we have used virtually unchanged for 4 years. A quartz cell, only quartz and Teflon parts, a helically wound platinum anode, 3 or 5 centimeter long, 3 millimeter diameter palladium cathode, 4 contacts for resistance ratios, sometimes a platinum pseudo-reference electrode. We keep this thing as simple as possible and keep the soluble parts as few as possible. Found myself with a very good workhorse. First point that I want to describe is the effects of annealing time. Our typical annealing procedure is 3 hours at 850 degrees in a low oxygen environment. That is a gated vacuum. 850 degrees, 2 to 3 hours. What we were trying to do in this particular experiment was to see if the annealing time had an important effect on loading. The purple curve shows our typical annealing process. The resistance ratio increases, goes through the maximum down the right-hand side, and at very low current densities, this loading continues to increase, the resistance continues to decrease over a period of time. You have to ignore the data where it says Bay Area, there was a poor contact. But at modest current densities, up to about 80 milliamps per square centimeter, the resistance ratio continues to go down for this purple cell, annealed for 3 hours, whereas the 2 examples annealed for 48 hours. Worse performance, faster loading, it got there faster, hit the maximum, and was relatively unchanged, did not respond to increasing current. My guess is that that annealing procedure, whatever the effective time was, whether it be metallurgical or impurity derived, the increase in contamination or structural change has caused some disbenefit to the loading process. The second point I was going to make is additives. Here, data presented by Alan Hauser previously. The yellow curve, loading through the maximum, then each of these steps indicate the time at which the current density has been increased. But what you can see on the first cycle, a strip here, the second cycle, a strip and aluminium addition, the third cycle, is that prior to aluminium additions, in every case when the current was increased, the resistance ratio first decreased, indicating improved loading, and then slowly with time the resistance ratio will head back on up, indicating the cathode is deloading. The addition of aluminium doesn't necessarily improve the instantaneously protects the cathode against deloading with time. Alan has taken the data in this set and superimposed them on the data in this set, the second and third loadings. You can see them overlaid here, so that load 2, no aluminium, as the current was increased, the resistance ratio decreased, that's good, increases, that's bad. With the addition of aluminium, identical current steps, the apparent, the immediate increase in loading is possibly even worse with aluminium additions. But what it is that these don't deload spontaneously with time. So aluminium is doing something on the surface to prevent whatever surface modification occurs with time, which leads to deloading. The effect of periodic, as a result of these two scripts, we call the apparently not well loaded cathode, the red one, became a better loaded cathode. So this stripping procedure does something to the surface which facilitates increased loading. Finally, the difference in the two lots. Lot 3 palladium, nominally identical to lot 2 palladium, and we're busily now searching to identify the metallurgical and or chemical differences between these two different lots. However, after a very long time of operation, loading, stripping cycles, additions of aluminium, the lot 2 material achieved a resistance ratio of about 1.5, indicating loading very close to 1. The lot 3 material achieved a resistance ratio of 1.7, which is a loading of about 0.9. So a very significant and systematic difference between these two different batches of palladium, one which results in good loading, one which results in poor loading. We've very much diversified our calorimetry. We've been carrying on with our mass flow closed cell calorimeters, which maintain high accuracy over very, very long times necessary for these experiments, and over a very wide range of input and output paths. And I'll describe the results of some of these cells in a minute. We also embarked on something that's new for us, heat flow calorimeters, which we are running mostly thermodynamically open. So we're running open heat flow cells in a mode that many of you have used over the years, but we have not. And we find that this system does result in significant advantages and disadvantages, of course. They're more sensitive in degrees per watt, and the time constants, the response times are very much faster, or can be very much faster in a heat flow system than a mass flow system with large amounts of moving water. Much greater flexibility afforded by the heat flow designs, flexibility of geometry, you can make big holes in the top of them through which you can put optical and nuclear detection systems. One of the advantages as we see it is that it allows for a redundancy of method, and one argument that one can never really beat. You do a single experiment one way and you always get the same result. No matter how many times you do that experiment, you cannot assert with complete confidence that there was no artifact in that experiment. If, on the other hand, you get the same result in an open cell with a heat flow calorimeter as you get in a closed cell with a mass flow calorimeter, then you can be reasonably confident that if there is an artifact that's producing the effect, it's not an artifact system. So we are very interested in diversifying our calorimetry and have done a great deal to do that. We've been operating isoparabolic cells, operating two different types of CBEC heat flow calorimeters, and a novel design, a lateral heat flow, which will be the subject of another paper another time. Describe some of the results in our labyrinth calorimeters. Basically run 4 this year, which we call L1 through 4. We use nickel anode for L1. In our hands, in our experience, we have never been able to satisfactorily load a cathode that had a nickel anode. Other people may have other results, but we we simply cannot get good loading if we use nickel anodes. It's unfortunate because nickel is cheaper, if nothing else, than platinum, but we abandoned the use of nickel in all of our cells. Second, platinum niobium anode, which we also found not to be especially satisfactory. Two cathodes, L3, L1 and L2, and batch 3 nickel hard material, which by itself does not give good loading. And the results from these two cells were essentially many hundreds or thousands of hours of calorimetry, and the cells maintained themselves within their thermal balance within sensitivity and accuracy of measurements, which is 50 milliwatts. These cells also run, as you see, rather high current densities and high currents, up to 6 amps, 1.6 amps per square centimetre. And the loadings that we obtain, L1 and L2, we got loadings of about 0.76. L3 and L4, we get loadings of 0.94 and 0.92 respectively, which is still in that cross-hatched region where you might get excess heating from. I should say that this experiments L3 and L4 just finished. They were very long experiments. We haven't finished analysing the results. I just want to draw attention to 3 details of the results of those cells, which I think bear on the discussion today, and very much bear on the things that Martin Fleischmann and Stan Pons have spoken about. I feel that everything we do in this field is unfortunately derivative of Fleischmann and Pons, and even our terminology. I've tried to make a change here, so rather than talking about boil off, I'm going to talk about boil on. Rather than talking about heat after death, I'm going to talk about heat after life. And we have invented the term, which he will later tell me that Euro's already thought of, loss of resistance. We've observed that after prolonged periods of loading, the palladium is less resistive at the end of the experiment than it was at the beginning, which is to me rather mysterious. Just to orient you, if you remember our old calorimeters, this is the object that's placed in the constant temperature bath, taking fluid from the bath past 2 temperature sensors, past the cell, past 2 temperature sensors, and out to the pumps. We've changed this design by the incorporation of a labyrinth, so the flow, instead of now coming in from the bottom and going up the top, comes in from the top and out to the top. The flow comes in from the bath past the same 2 temperature sensors, goes down this inner wall, in through the labyrinth, round the bottom, past the cell, up through fluted flow path, picking up the heat from the cell and then back out the top. By incorporation of this change and some other changes, we were able to get the conductive component of heat flow from the system down below 1%. So this machine, 99+% of the heat is conveyed as temperature rises in the water. Less than 1% is lost by radiant or conductive methods. So very nice result. This is a section of data from L2. Nothing succeeds actually as a blank for these experiments, as well as cathode, which doesn't load. And we ran these 2 cells for very long times and were able to establish the stability and accuracy of the calorimeter for no other reason than we had not obtained sufficient loading in these particular cells to obtain any excess heat, to observe any excess heat at least. So these are raw data, in fact, without the non-steady state correction, which reduces this apparent scatter markedly, in fact. We're looking at raw data for the 2 independent pairs of temperature sensors. You can barely see them because they overlap. The calorimeter maintained itself within this plus or minus 100 milliwatts, plus or minus 50 milliwatt segment of 0 for the entire duration of the experiment. So when there is nothing, we can see nothing well. This is going to few slides which describe this this describes this boil-on phenomenon. Here's a time late in the experiment, 1880 hours. These time markers are 24 hours, so a day. each one of these markers. The black is the total system power. We run our calorimeters in what we call a constant power mode, where the computer determines the electrochemical power, here represented by the red line, and adds to it an amount of power in a control heater, here the blue line, such that the sum of them is the control value. At this point, we simply stepped the control value from 50 to 55 watts. A lot of watts, a lot of current density. Here the current density is about 1.35 amps per square centimeter. At this point, something that we had not planned occurred, and is in many cases, and happens in many cases. It taught us something that we, I think, might very well be important. The inlet flow was blocked by a small piece of black plastic which happened to be floating in the bath for reasons which I won't go into, so that the mass flow decreased. The system was putting in 60 watts, but now the rate of cooling was reduced. What happened was the temperature went up, the electrochemical power came down because the resistance of the electrolyte decreased. The heater compensated almost perfectly. You can see a little wiggle here, so that the constancy of power was maintained, but the electrolyte got very hot. This is the same region of time. Here is the calculated baseline excess power for this event. The mass flow blockage occurred at this time. Here I'm showing the mass flow rate in black, and the blue referred to the left scale, purple black as it is on your list. Electrolyte temperature increased, in fact, to a value of about 103 degrees at its largest value, as also did the excess power. So as the electrolyte temperature went up, the excess power went up fast. As the quirks of nature have it, the system was never designed for the outlet temperature sensors to record a temperature as high as they were as they observed, so that as the excess power goes up, the electronics in the system shut the temperature sensors down, so we now became blind to the excess power. I'm going to show you a blow-up of this region. We're saved a little bit in the fact that we were recording the electrolyte temperature, that is the blue line. We can calculate in some sort of isoparabolic mode what the power generation rate inside the cell was by knowing what the temperature of its boundary is and what the temperature of the electrolyte is. So I have a crude isoparabolic calorimeter which I can use to calculate the power and maybe retrieve the missing information. Here is calculation shown in green superimposed upon the calculation from the mass flow rate. They superimpose approximately, giving me confidence that this calculation of power is at least reasonably accurate. So that when we scrutinize this region, this is the point at which the mass flow rate blockage occurred. The magenta points are the excess power calculated by the conventional mass flow calorimetric calculation, going up to values of about 8 watts of power excess. The green line is this kludged isoparabolic calculation of excess power based upon the electrolyte temperature sensor, the dashed purple line here. And this value parallels that. The excess power calculated by this means parallels that of the excess power calculated in the mass flow calorimeter, and then proceeds beyond the point at which the temperature sensors shut themselves off to a value of about 16 watts. Now this is, in Fleischmann-Pons terms, this is not a spectacular amount. There's about a third of a cc of palladium there, so it's less. It's about, even at 16 watts of excess power, we've got about 100 watts excess per cc of palladium. It's not a prodigious amount. And this is 16 watts in 60 watts, so as a percentage it's not large, but it's nevertheless a fairly large effect that seems to have been stimulated by a rapid increase of the electrolyte temperature and therefore the cathode temperature, much in the way that Martin described one ought to do one's experiments. It's a shame that we only found out about it by accident. Maybe we should pay more attention. One of the other interesting things about this observation, and I see I'm running over time, is that the loading didn't substantially decrease during the time when this cathode got very, very hot. The loading was at a value of a little bit less than 0.9, if you can read these scales. The current density was increased. The loading increases with the increasing current density in the way that it typically does. It responds to the ramp and then continues to increase for a considerable period of time after the current density ramp is finished. In this case, the loading seems to be more or less spontaneously increasing by itself at a time of constant current input. This is the region of time that I just discussed. It could be that the loading tried to come down a little bit from 0.92 down to the direction of 0.9, but it also might be that I'm simply underestimating the resistance of the cathode, which would also cause the apparent loading to decrease. But in any case, after the event's all over, within a day, the loading of the cathode is the same as it was before. It is going up. Finally, revealing. Heat afterlife. It's apropos to the question that was asked at the end of the last speaker. The end of the experiment. Current densities have been very large for a very long time. The loading has been maintained at a relatively high value for a significant period of time. The end of the experiment, we stepped the current density down from 1600 milliamps per square centimeter to 23 milliamps per square centimeter to do our post-test calibrations. So this 23 milliamps per square centimeter is a small current density below that value which we would normally expect to see excess power. That is a very, very small amount of electrochemical input current. Nevertheless, the excess power, which is represented in pink by this jagged curve here, it comes down, yes, it doesn't come down to zero, it comes down to about 200 milliwatts. And then as these days march by, in 4 or 5 days, this excess power drifts down towards zero. At this point, we reverse the polarity, or at least we turn the current down from 23 milliamps per square centimeter cathodic to 1 milliamp per square centimeter anodic. Electrolyte temperature sensor comes down. The sensitivity of the color emitter is such that we can now no longer observe any excess power. It seems to have merged with the baseline. But the cathode electrolyte temperature sensor drops rapidly to its equilibrium value. This is being bathed continuously in water drawn from the bath at 29.96 degrees centigrade. And yet, the cathode, the electrolyte sensor near the cathode drops and continues to drop over a very, very long period of time, suggesting that even while the cathode is being subjected to an anodic stripping current density, albeit small, and the loading is going down, and a long time after the cell has ever experienced high current densities, there seems to be a residual decrease in the temperature sensed in the vicinity of the cathode. Final point, and I will stop. Loss of resistance business, which I present as more of a mystery than a contribution to your understanding. At the end of the experiment, we typically stripped all of the hydrogen out just to facilitate in the post-test analysis so that you don't have the hydrogen molecular ion contributions to the SIMS analyses. We always find the resistance at the end, after we've stripped all the hydrogen out, is within 1% of the resistance of the cathode at the beginning. Unless something untoward has happened, such as cracking. In this case, we subjected this particular cathode to a very significant strip. It was being stripped at 1.1 amps per square centimeter, so that the cathode at this point was made anodic. The voltage follows this profile in response to this green profile of current density. The resistance ratio, instead of coming down and asymptotically approaching this value of 1, indicating that the resistance at the end is the same as the resistance at the beginning, goes through 1 down to a value of 0.7. This we didn't believe. We reversed the current, the cathode reloaded again, we stripped it out again, this time more gently. And indeed, when we took this cathode out, cut all the wires off it, measured it on the bench with the same instrument that we measured it in the beginning, the resistance of this particular piece of palladium at the end of the experiment is only 0.7 of its value at the beginning. Of this, for this, I have no explanation. Thank you.
You got into the region of film boiling. You were running this thing galvanostatic. Would the voltage then be going all over the place and it would be difficult to measure the power? Or have a wrong picture of what's going on?
The voltage was being recorded continuously in our normal manner. It didn't seem to be unduly perturbed. You can tell exactly what it is. The slide that I put up of the input power shows the electrochemical power, which is simply the product of the current and the voltage, and there is no significant amount of oscillation or variation on that voltage value. And the ripple that you observe on the voltage increases with current and will also increase with boiling, presumably, but it's always a value of a fraction of a percent of the mean value of the voltage.
I would like just to comment the similarity of your results with the results I presented before. Also, even if the experimental situation is different, in my case, I have a secondary current which acts as a confinement current, and also in this case, at constant electrolysis current, we have a change of the resistance of the electrode, which go in the same direction as you show, because I am not a direct measurement of the loading. You have a direct measurement of the loading, but the final effect seems the same.
I agree. If there are no other questions, there is one brief presentation to be made now by Mr. Matsui, who will describe a new research center established, or to be established in Japan.
Sorry for disturbing you to go to lunch, but forgive me and please give me just 5 or 10 minutes. I'm honored to be here to announce you that we in Japan have decided to establish this one, new hydrogen energy research project. You might be surprised and confused with the name of new hydrogen energy. This is our official terminology regarding to so-called cold fusion or whatever this a little bit strange phenomenon. And then outline of the project is this. Purpose to clarify the feasibility of this phenomenon as one of the future energy sources. To confirm this, two components we do have. One is to confirm and demonstrate an excess heat generation phenomenon. And secondly, to make an excess heat generation this phenomenon not occur. And the second purpose is to promote the project cooperatively with overseas institutions and think that the majority of the academia or whatever society is not yet regarding this phenomenon as science yet. That's our standpoint. If, therefore, we need an open environment where we can talk about, discuss about the result and so forth, therefore, we try to make our project open as much as possible. Period from this November to March 1997, it means 3 years and 4 months, or 5 months. And the approximate budget, presently we assume $30 million equivalent. But it's a request base, therefore we may get less because of the present days very hard situation in the economy, especially in Japanese government. But we would like to get this amount. But this is the scheme of the national project. We had this meeting, and then NEDO, New Energy and Industrial Technology Development Organization, and we got a contract with them. Myself, the Institute of Applied Energy, and then we have established the R&D Center for New Hydrogen Energy inside this institute, November 1st. I mean, just 1 month ago. And then just 5 days ago, we have established New Hydrogen Energy Laboratory in Sapporo. Today, another staff, colleagues of my center are working to settle down the 2 sets of equipment in that laboratory. And then this weekend, we will work for setting up the equipment together with Professor Weissman and Professor Mons, and then hopefully Dr. Kunimans. This is the brief exploration of the possible or expected activities at the laboratory. This is the brief exploration of the presently conceived schedule of the project. But I may say, at the end of the fiscal year 1994, we are planning to have a peer review of what we are going to do, what we will get at that time. Then we'll decide to expand our activity or stay on as it is for a moment, or remain back to the more basic, or shut down our project. We will have intermediate reviewing here. We do have, our center will have 2 activities. One is national project. The second one is this, we call it multi-track project. We collect the fund from the private industries, from Japanese leading companies, like electric utilities, and then gas company, and then leading manufacturers, and whatever. And then we distribute those monies to the universities to conduct much more basic studies. And then the head of the universities will be, is Professor Okamoto of Tokyo, Technology of Tokyo. This is the brief explanation of what's going to be done at the universities. This is the general idea of our effort. Left-hand side, experimental studies at Sapporo laboratories. Right-hand side, basic studies at the universities. Combine those efforts through the support of the cooperation programs. Some of them may be international one for this project. Our project is, the basic concept is like this one.
teacher.